What if the universe in its breathtaking and silent immensity is waiting for you, not just for you to witness it, but for you to give it form, to grant it definition through the simple act of looking? This is a question that sounds less like physics and more like a riddle from a forgotten mythology, yet it haunts the deepest corridors of modern science. We live our lives cushioned by a profound and reassuring assumption that the world is simply times their asterisk. The chair you are sitting in possesses a definite location. The Earth continues its silent orbital dance around the Sun, whether a single human mind is aware of it or not. The moon, that lonely pockmarked sentinel of our night, hangs in the void, a solid, tangible sphere of rock and dust, its existence an unshakable fact. Our entire civilization, every bridge built, every equation solved, is constructed upon this bedrock of objective reality. A belief in a single, shared, and stable universe that exists independently of its inhabitants. It is the ultimate constant, the grand stage upon which the chaotic drama of life is permitted to unfold. But what if this fundamental comfort is a grand illusion? What if the bedrock is not solid rock, but a shimmering, uncertain sea of pure potential? For centuries, this was the unquestioned dream of science. From Newton, who imagined a clockwork cosmos governed by unbreakable laws ticking away with perfect divine precision, to Einstein, who searched tirelessly for a final theory that would describe a complete and objective reality. The goal was always the same: to read the universe's blueprint. We saw ourselves as cosmic cartographers, meticulously charting a pre-existing territory. The mountains, the rivers, the continents of existence were all there, waiting to be discovered and inked onto our maps. Our observations, we believed, were passive. We were merely pulling back a curtain to reveal a spectacle that was already in progress, a performance that began with the Big Bang and would continue long after we were gone. In this classical view, the universe is a story already written, bound in a single colossal volume. Our job as physicists and as human beings was simply to learn how to read its language. The properties of a planet, its mass, its spin, its momentum, were as real and as intrinsic as the words on a page. They were absolute truths waiting patiently in the dark for the torchlight of our inquiry. This vision of the cosmos is orderly, it is predictable, and above all, it is profoundly reassuring. It gives us a sense of place, a sense of solid ground beneath our feet in an otherwise infinite and indifferent void. It is the world of our senses, the reality we touch and see and feel every moment of our waking lives. Then, at the dawn of the 20th century, we pushed open a door, and the familiar, comfortable room of classical physics gave way to a landscape of impossible strangeness. We peered into the heart of the atom, the fundamental building block of everything we thought was so solid and real, and the blueprint we expected to find dissolved into mist. The solid ground beneath our feet crumbled into a quantum fog of probability and paradox. Down here in the subatomic realm, the rules of our world no longer applied. Particles, the supposed elementary constituents of reality, refused to be pinned down. An electron, we discovered, was not a tiny, discrete ball of matter orbiting a nucleus like a planet around a sun. Instead, it existed as a hazy cloud of potential, a wave of probability smeared across space. It was in a sense everywhere and nowhere at once, a ghost in its own machine, only condescending to choose a single definite location when we forced its hand, when we performed the act of measurement. This was the principle of superposition. A concept so bizarre, so contrary to all human intuition, that it felt like a violation of logic itself. How could something be in multiple states
Soaring
simultaneously?
through the stars,
It was like saying a coin is both
by the
heads
light
and
of the
tails while it is
supercluster.
spinning, but the quantum coin impossibly remains in that spinning state until the very instant it lands. The act of looking, of interacting with it, seemed to conjure its reality into being from a ghostly menu of possibilities. And the strangeness only deepened. We found that particles could become linked, entangled across vast distances of space. Two photons born from the same event could fly apart to opposite ends of the galaxy, yet remain mysteriously connected. Measure a property of one like its spin, and you would instantly know the corresponding property of its distant twin. It was as if they were communicating faster than the speed of light, a spooky action at a distance, as a deeply unsettled Einstein would call it. This quantum world was not the elegant, predictable clockwork of Newton. It was a shadowy, probabilistic casino where God, it seemed, was not only playing dice, but was also rigging the game in ways we could barely comprehend. The very foundation of our objective universe, the idea that things have definite properties independent of us, was beginning to crack. For decades, physicists wrestled with this profound crisis. The dominant answer, which holds sway to this day, became known as the Copenhagen interpretation. It offered a pragmatic, if philosophically unsettling, truce. It proposed a universe divided into two separate domains: the weird, probabilistic quantum world of particles and the familiar classical world of our everyday experience. The act of measurement, the theory stated, was the bridge that connected them. When a quantum system, like an electron in its hazy cloud, is measured by a large classical device, its wave function, that cloud of all possible realities, instantaneously collapses. One single reality is chosen from the menu of possibilities, and the electron suddenly appears at a specific point. The ghost solidifies. A spinning coin lands, but this explanation felt to many like sweeping the mystery under the rug. What exactly is times a measurement? What is the magical ingredient in an observation that forces the universe to make a choice? Does it require a conscious human observer, a Geiger counter, a dust mote? The theory provided no clear, dividing line, leaving us with a schizophrenic view of existence. One set of rules for the small, another for the large, with an arbitrary, poorly defined border in between. It asked us to accept that reality fundamentally changes its nature simply because we decided to look at it. This was a pill too bitter for many to swallow, including Einstein. He argued passionately that quantum mechanics, for all its predictive power, must be an incomplete theory. There had to be a deeper reality, a set of hidden variables that would restore order and predictability to the cosmos. "I like to think the moon is there," he famously remarked, "even if I am not looking at it." He was voicing the deepest intuition of the human mind, the yearning for a solid, independent reality. The Copenhagen interpretation, in a sense, told us to stop asking such questions. "Shut up and calculate" became the unofficial motto. The equations worked, predicting the outcomes of experiments with stunning accuracy. For most working physicists, that was enough. But for a few, the nagging philosophical abyss remained. The crisis was not solved, it was merely postponed. The question of what reality times is times when we are not measuring it was left unanswered, hanging in the air like a discordant note in an otherwise beautiful symphony. And now, from the heart of that lingering disquiet, a new idea, as radical as it is elegant, has emerged. It suggests that the problem isn't with our theories, but with our most foundational question. We keep asking, what is the true, absolute state of the universe? This new perspective whispers a revolutionary answer. There is no such thing. This is the central insight of Relational Quantum Mechanics, or RQM, a framework developed by the physicist Carlo Rovelli. It proposes a breathtaking shift in our understanding of existence. It tells us that the properties of any object in the universe, its position, its momentum, its spin, its very reality, are not intrinsic absolute qualities. They are not labels permanently attached to that object. Instead, properties exist only in the relationship, in the interaction between one physical system and another. Think of a simple conversation. The words you speak have meaning only in relation to the person listening. The information exists times between times you. It is not an absolute property of you nor of the listener, but a shared relational phenomenon. RQM suggests that the entire universe works this way. An electron does not have times a definite position. It has a definite position times with respect to you, times when you interact with it. It has a definite position times with respect to a detector times when it collides with it. It has a definite position times with respect to another particle times when they bounce off one another. But when you ask what is its position when nothing is interacting with it, RQM gives a stunning reply. The question is meaningless. It is like asking for the sound of a one-handed clap. It is like asking for the east side of a sphere. The property simply does not exist without the relationship that defines it. This simple, powerful idea dissolves a century of paradoxes. The infamous collapse of the wave function vanishes. There is no magical moment of collapse because there was never a single absolute wave function for the entire universe to begin with. When you measure an electron, its properties become definite times for you, asterisk. Your interaction has updated times your time's information about it. But for another observer, someone who has not yet interacted with your experiment, the electron remains a cloud of potential. Your reality, the one you have just co-created through your interaction, is not the same as their reality. And this is not a subjective statement about psychology or belief. It is a physical description of a world where reality itself is perspectival. Each interaction is like a new sentence being written in a cosmic story, a story that is unique to the participants of that interaction. There is no master narrator, no God's eye view from outside the system that sees the one true state of things. There are only participants. We are not passive observers of a pre-written cosmic script. We are co-authors, and every glance, every touch, every measurement is an act of writing that script into being, defining reality from our own unique perspective. This is a universe stripped of its absolute foundation. The solid stage upon which we thought we were acting has dissolved, replaced by an infinite shimmering network of relationships. Nothing is real in and of itself. Everything is real only in context, in dialogue with something else. The solidity of the chair you are sitting on is a manifestation of countless trillions of quantum interactions happening every nanosecond between the atoms of the chair and the atoms of your body. Its chairness is a relational property, a stable consensus emerging from an ocean of interactions. The moon, that ultimate symbol of objective reality, is not simply there in an absolute sense. Its properties, its position, its albedo, its gravitational pull are defined by its network of relations. Its position is defined relative to the Earth, relative to the Sun, relative to the photons of light that travel from it and strike your eye. Each interaction updates the story, painting a new detail onto the canvas of reality from a specific point of view. When no one and nothing is interacting with it, it reverts to that quantum haze of pure potential, its story waiting for the next reader to open the book. This relational tapestry is woven from the quantum threads of information. When two systems interact, they exchange information, and in that exchange they define one another. Reality is not a collection of things. It is a ceaseless, dynamic process of interaction. It is a symphony that only exists in the playing, where each note draws its meaning from the notes that surround it. To be is to interact. To exist is to be in relation. This is a profound and humbling vision. It dethrones us from our privileged position as spectators looking in on the universe from the outside. It forces us to accept that we are fully embedded within it, participants woven into the very fabric of reality we seek to understand. Our knowledge of the world is not a map of a foreign territory. It is a part of the territory itself. The line between the observer and the observed, a line that has defined the very practice of science, blurs and disappears. So this is our journey. We will venture into this new relational cosmos, a world without absolutes, a reality dependent on perspective. We will explore the mind-bending implications of this idea for our understanding of space-time and even consciousness. If my reality is woven from the threads of my interactions, what about yours? How do our separate perspectival realities combine to create the shared world we all seem to experience? Are we living in the same universe at all, or are we each dwelling in a bubble of reality defined by our personal? The history of interactions, bubbles that just happen to overlap most of the time. And what happens at the frontiers of knowledge, at the event horizon of a black hole? Or in the first fleeting moment of the Big Bang, where interactions are so extreme that our stories might radically diverge? The questions are as vast as the universe itself. They challenge not just our physics, but our philosophy, our sense of self, and our place in the cosmic order. The search for objective reality may have been a noble quest, but perhaps it was a search for something that was never there. Perhaps the real truth is far more intimate, far more participatory, and far more astonishing. The universe isn't just out there. It is in here, born in the delicate, fleeting, and powerful dance of relation that connects us all. What if the chair you are sitting on is not truly there? Not solid, not definite, not occupying a unique place in space and time until the moment your awareness registers its presence. This idea feels absurd, a violation of every intuition we hold dear, an affront to the bedrock of common sense. For centuries, our understanding of the cosmos was built on a foundation of absolute certainty, a magnificent and reassuring architecture of objective reality. In this classical universe, the grand stage envisioned by giants like Isaac Newton, the cosmos, was a breathtakingly intricate clockwork mechanism. Every star, every planet, every grain of sand moved according to immutable, discoverable laws. Reality was a performance that unfolded with perfect predictability, whether there was an audience to witness it or not. The moon does not cease to exist when a cloud obscures it from view. A tree falling in a forest most certainly makes a sound, even if no ear is there to hear it. This was a universe of solid objects and unwavering trajectories, a cosmos governed by a logic as pure and unyielding as mathematics itself. We humanity were merely the fortunate spectators. Our role was to discover the blueprint of this grand design, to trace the gears and levers of the cosmic machine. The French mathematician Pierre-Simon Laplace gave this deterministic dream its ultimate expression. He imagined a vast intellect, a demon that could know the precise location and momentum of every single particle in the universe at one instant. For such an intellect, he declared, nothing would be uncertain. The future, just like the past, would be present before its eyes. This was the pinnacle of the classical worldview, a universe as a solved equation, a story already written from the first page to the last. Our consciousness, our act of observation, was utterly irrelevant to the unfolding of its plot. We were observers standing safely on the riverbank, watching the relentless and unchangeable current of reality flow by. We could measure the river's speed and map its course, but we could never ever alter its path simply by looking at it. This was a profoundly comforting thought, a philosophical anchor in the vast, often frightening emptiness of space. The universe was real, it was independent, and it was in principle completely knowable. It was a cathedral of granite certainty, and for a time, we felt we had found its keys. But at the dawn of the 20th century, as physicists began to probe the very smallest constituents of this grand cathedral, they found that its foundations were not made of granite at all. They were built upon something far stranger, a substance that seemed to shift and shimmer like mist. The first fissures in that perfect classical facade appeared in the realm of light. For centuries a debate had raged: was light a stream of tiny particles, or was it a continuous wave like a ripple spreading across a pond? The evidence for waves had become overwhelming, beautifully demonstrated by a simple yet profound experiment first conceived by Thomas Young. When you shine a light through two narrow parallel slits, it doesn't just create two bright spots on the screen behind them. Instead, it produces a complex pattern of many light and dark bands, an interference pattern. This is the unmistakable signature of waves. Where the crests of the waves from each slit meet, they reinforce each other, creating a bright band. Where a crest meets a trough, they cancel out, creating darkness. It seemed a settled matter. Light was a wave. The story, however, was about to take a deeply unsettling turn. When physicists developed the technology to send not a continuous beam of light, but individual particles of light, photons one at a time, they expected the wave behavior to vanish. Imagine firing single bullets at a wall with two openings. You would expect to find two clusters of bullet holes on the backstop, one behind each opening. Nothing more complex. And yet when they fired single photons one by one, a ghostly interference pattern began to build up over time. It was as if each individual photon, traveling completely alone, was somehow passing through times, both slits simultaneously, times, and interfering with itself. This was nonsensical. A single particle cannot be in two places at once. It was a paradox that struck at the very heart of what it meant to be a thing. The universe at its most fundamental level seemed to be breaking its own rules. The mystery only deepened, becoming an abyss of incomprehensibility when the physicists decided to watch. They placed a detector at the slits, a tiny electronic eye, designed to see which of the two slits each photon actually passed through. The moment they did this, the moment they measured the photon's path, the ghostly behavior vanished. The interference pattern disappeared, completely replaced by two simple bands, exactly as one would expect from bullets. It was as if the universe knew it was being observed. The very act of gaining information about the photon's path forced it to abandon its wave-like ambiguity and behave like a simple, well-defined particle. It had to choose a single slit. This was the birth of wave-particle duality, a concept so bizarre it defied all classical intuition. An electron, a photon, any fundamental entity was not one thing or the other. It was somehow both a phantom that chose its form depending on the questions we decided to ask of it. Reality at the quantum scale was not a fixed object to be passively observed. It was an elusive dance, and our observation was a part of the choreography. This led to an even more radical idea, one that would tear down the very concept of a definite state of being superposition. Before an observation is made, quantum theory states that a particle does not have a definite position or momentum or spin. It exists in a probabilistic haze, a weighted sum of all its possible states at once. The electron hasn't chosen a path. It is in a very real sense a ghost of all possible paths. Its reality is described not by a single number but by a mathematical object called a wave function, a cloud of potentiality, a spectrum of possibilities. It is not here nor there. It is here times and times, there and everywhere else it could possibly be, all at the same time. The solid, predictable world of Newton was dissolving into a fog of maybes. The act of measurement then became something almost magical. When we look, this cloud of possibilities instantly collapses into a single concrete reality. Out of an infinity of what-ifs, one what-is suddenly springs into existence. But how and why? What was so special about the act of measurement that it could conjure a single solid reality from a ghost of probabilities? This profound weirdness fractured the community of physicists, leading to one of the greatest intellectual battles of the 20th century. The conflict was personified by two towering figures, close friends, whose debate would define the meaning of reality for generations to come. On one side was Niels Bohr, the Danish physicist and philosophical patriarch of the new quantum mechanics. Bohr was a pragmatist, almost a mystic. He argued that we must abandon our classical attachments to an observer-independent reality. The quantum world, he contended, simply is not visualizable in our everyday terms. The strange rules, the superposition, the collapse of the wave function, this was not a sign of an incomplete theory. This times was times the theory. The properties of a quantum system, like the position of an electron, simply do not exist in any meaningful sense until they are measured. He formulated what became known as the Copenhagen interpretation, a view that essentially told physicists to stop asking unanswerable questions. The mathematics worked. It made stunningly accurate predictions. The role of physics was not to describe what reality times is times, but to describe what we can times say times about reality through our experiments. Before the measurement, any question about the electron's true location was for Bohr meaningless. It was like asking about the marital status of the number 7. On the other side stood Albert Einstein, the architect of relativity, the man who had redefined space and time, and the ultimate defender of objective reality. Einstein found Bohr's interpretation utterly abhorrent. While he acknowledged the stunning predictive power of quantum mechanics, he could never accept that the universe was fundamentally probabilistic and observer-dependent. For him, the theory was a magnificent provisional success, but it was incomplete. It was a statistical approximation of a deeper, more deterministic reality that we had not yet uncovered. The fuzziness, the probabilities, were not features of reality itself, but reflections of our own ignorance. There must be, he insisted, hidden variables, local underlying properties of the particles that determine the outcomes of our measurements in advance. We just couldn't see them yet. His deep-seated belief in a rational, ordered cosmos was captured in his famous, almost desperate pronouncement: God does not play dice with the universe. He believed in a reality that was there, solid and whole, whether we were looking or not. The moon, he once quipped to a fellow physicist, is most certainly there, even when I am not looking at it. Their legendary debates, carried out in person at the Solvay conferences and in a series of published thought experiments, were a clash of titans, fighting for the very soul of physics. Einstein would relentlessly attack the new theory, devising ingenious scenarios designed to expose its logical absurdities and internal contradictions. He tried to show that one could in principle measure a particle's properties without disturbing it, violating the core tenets of the Copenhagen view. Bohr, with his brilliant and often inscrutable reasoning, would reportedly stay up all night dissecting Einstein's arguments, and would return the next morning with a rebuttal time and again demonstrating how Einstein's classical thinking failed to grasp the revolutionary logic of the quantum world. This was more than a scientific disagreement. It was a profound philosophical schism. Einstein was searching for the universe's eternal blueprint, the complete and unchanging score of the cosmic symphony. Bohr was arguing that there is no pre-written score. The music is composed in the very act of listening to it. For Bohr, the observer was not a passive audience member, but a crucial participant whose choice of what to measure helped co-create the reality being measured. This epic struggle brought the central agonizing mystery into its sharpest focus, the measurement problem. The equations of quantum mechanics describe the world in two fundamentally different ways. As long as a quantum system is left alone, its wave function evolves smoothly and predictably, a beautiful, continuous wave of spreading possibilities. But the moment a measurement is made, this elegant evolution is violently interrupted. The wave function instantaneously collapses into a single, definite state. The problem is that the theory itself gives us no clue as to what constitutes a measurement. What is the magical dividing line, the so-called Heisenberg cut, that separates the strange probabilistic quantum world from our familiar certain classical world? Is it the interaction with a large measuring device? Does the device itself exist in a superposition until its reading is noted? Does it require a conscious observer, a human mind, to collapse the wave function and turn potentiality into actuality? This question was not just a footnote, it was a gaping wound in the theory's conceptual heart. The sheer absurdity of taking the Copenhagen interpretation to its logical conclusion was famously captured by the Austrian physicist Erwin Schrödinger in 1935. Frustrated by the strange implications of his own equations, he devised a thought experiment that has haunted physics ever since Schrödinger's cat. Imagine a cat placed in a sealed steel box along with a diabolical device. In the box is a tiny amount of radioactive material so small that in the course of 1 hour there is an exactly 50% chance that a single atom will decay. If it decays, it triggers a Geiger counter, which in turn releases a hammer that smashes a flask of hydrocyanic acid, killing the cat. If the atom does not decay, the cat remains alive. The entire system is sealed off from the outside world. According to the standard quantum rules, until an observation is made, the radioactive atom is in a superposition of both decayed times and times not decayed. But because the cat's fate is inextricably linked to the atom's state, the cat itself must also be in a superposition. It is not that we simply don't know if the cat is alive or dead. According to the theory, the cat is quite literally both alive times and times dead, simultaneously, a ghostly blend of two contradictory realities. It is only when we open the box, when we make a measurement, that the wave function of the entire system collapses and reality is forced to choose. We find either a living cat or a dead cat, but never both. Schrödinger intended this as a ridiculous parody, a demonstration that the quantum description of reality could not possibly be the whole story when scaled up from the microscopic to the macroscopic world, and yet the mathematics held firm. The paradox wasn't a flaw in the logic, it was the logic itself. Where does the quantum weirdness stop and our classical reality begin? What is the special power of our observation that it can resolve this grotesque state of feline limbo into a definite outcome? For decades, this problem festered often, relegated to the realm of philosophy, because there seemed to be no way to test the competing visions of Bohr and Einstein. Einstein's idea of a deeper hidden reality and Bohr's observer-created reality seemed to make identical experimental predictions. The debate was a stalemate, a philosophical impasse. Einstein would go to his grave believing that quantum mechanics was a stepping stone, not the final word, convinced that a more complete theory would one day restore the objective clockwork universe he held so dear. His final great descent was a concept he derisively termed spooky action at a distance, a consequence of the theory he felt was its ultimate absurdity. its final proof of incompleteness. But he had unknowingly identified the very clue that would decades later allow us to put reality itself on trial. The stage was set for a confrontation not of ideas but of experimental fact, a confrontation that would either restore Einstein's solid universe or shatter it forever. And so we were left teetering on a precipice, staring down into an abyss that defied a century of classical intuition. We had uncovered a subatomic world governed not by concrete certainties but by ethereal clouds of probability. A world where particles could exist in multiple states at once, their identities a ghostly smear of potential until the moment of observation. But this monumental discovery, which should have been a triumphant peak in human understanding, instead opened a chasm in the very foundation of reality itself. It presented a paradox so profound, so unsettling, that it threatened to cleave physics in two. For if the building blocks of our universe are fundamentally uncertain, how does the solid, definite classical world we experience ever emerge from them? How does the shimmering ghost of possibility solidify into the cold, hard fact of existence? This question is not merely academic. It is a direct assault on our most basic assumption about the universe, that there is a single objective reality out there, existing independently of us. To truly grasp the scale of this crisis, we must venture into the realm of thought, into an imaginary laboratory crafted by the mind of Erwin Schrödinger in 1935. He wasn't trying to prove quantum mechanics. He was trying to show its utter absurdity when scaled up from the atomic to the everyday. He asks you to imagine a box sealed completely from the outside world. Inside this box you place a cat. Alongside the cat you place a diabolical device, a single radioactive atom. This atom is governed by the laws of quantum mechanics. Over the course of 1 hour there is a precise 50-50 chance that it will decay. If it decays, it triggers a Geiger counter. The Geiger counter in turn is wired to a hammer, which will swing down and shatter a vial of poison, instantly killing the cat. If the atom does not decay, the cat remains unharmed. We seal the box and wait 1 hour. Now we must ask the question that tears reality apart. What is the state of the cat? According to our classical intuition, the answer is simple. The cat is either alive or it is dead. We just don't know which until we look. But quantum mechanics gives a profoundly different and deeply disturbing answer. The unobserved radioactive atom is not in a definite state of decayed or not decayed. It exists in a quantum superposition of both states simultaneously. It is a perfect blend of both possibilities. And because the fate of the entire system, the Geiger counter, the hammer, the poison, the cat, is directly linked or times entangled, times with the fate of that single atom, the entire system must also inherit this quantum weirdness. The hammer is simultaneously fallen and unfallen. The poison is both released and contained. And the cat, therefore, must be described by a wave function that represents it as being both 100% alive and 100% dead at the very same time. It is a conclusion so contrary to our experience that it feels like a violation. A cat is a complex macroscopic being. It cannot be a ghostly amalgam of life and death, and yet the mathematics of quantum theory are unrelenting. As long as the system remains isolated, as long as no information about its state leaks out into the wider universe, it must be described this way. The superposition holds. The moment we open the box to check on the cat, however, everything changes. In that instant, this cloud of overlapping possibilities appears to collapse. The wave function which held both outcomes in its embrace seems to snap into a single definite state. We find either a living cat or tragically a dead one, never both. Never some gruesome mixture. The act of measurement, the simple act of looking, seems to force the universe to make a choice. This is the infamous measurement problem. What is it about an observation that wields such incredible power? What mysterious force unleashed by our glance can wrestle reality from the jaws of ambiguity? Is it the light from our flashlight bouncing off the cat? Is it the interaction with the complex neurons in our brain? Physicists grappled with this, proposing that the collapse was triggered by any interaction with a large classical measuring device. But this just pushes the problem back a step. What makes a Geiger counter classical? It, too, is just a collection of atoms, each one governed by quantum laws. Why should it have the privileged status of an observer capable of collapsing a wave function while the radioactive atom does not? The line between the quantum and classical worlds seemed utterly arbitrary, a blurry, undefined border drawn in the sand simply for our own convenience. There was no clear definition of what constituted a measurement or who or what qualified as an observer. The theory gave us incredible predictive power, the most successful scientific theory in history. Yet it remained silent on the very process that connects its probabilistic mathematics to the singular reality we all perceive. The universe, it seemed, was playing a shell game, and we had no idea how the trick was done. Just when the paradox seemed contained within Schrödinger's imaginary box, another physicist, Eugene Wigner, deepened the nightmare. He took Schrödinger's thought experiment and added a terrifying new layer of complexity, a layer that implicated consciousness itself. Wigner asked us to imagine the same setup, the box, the cat, the deadly atomic trigger. But this time he places a scientist, we shall call her Wigner's friend, inside the laboratory with the box. The friend's job is to open the box at the appointed time and observe the state of the cat. The entire laboratory, however, is sealed off from the outside world. Wigner himself stands outside the sealed lab waiting. From Wigner's perspective, his friend inside is now part of the quantum system. Just as the cat became entangled with the atom, the friend's state now becomes entangled with the cat. After 1 hour, the friend opens the box. From her perspective, the mystery is over. She sees a definite outcome, a living cat, let's say. For her, the wave function has collapsed. She jots down in her notebook, the cat is alive. Reality for her has solidified. But what about Wigner, standing outside the sealed laboratory who has received no new information? For him, the entire laboratory containing the box, the cat, and now his conscious observing friend, is one vast, unobserved quantum system. According to the strict rules of quantum mechanics, Wigner must describe his friend as being in a superposition. A superposition of friend who has seen a live cat and friend who has seen a dead cat. It is a truly bizarre state of affairs. Wigner must consider his colleague to be in a smeared-out state of potential, her mind holding two contradictory beliefs simultaneously, until the moment Wigner opens the laboratory door and asks her what she saw. This thought experiment drives a stake through the heart of objective reality. Inside the lab, the friend experiences a definite event at a specific time. She would insist reality collapsed the moment she looked. But for Wigner outside, that same reality remains a ghostly probability cloud. So we must ask, when did the wave function times actually collapse? Was it when the Geiger counter clicked? When the friend's photons hit her retina? When the electrical signals reached her brain? Or did nothing truly happen until Wigner, the external observer, became involved? This creates a horrifying infinite regress. What if another observer outside Wigner's entire university was observing Wigner? Would Wigner and his friend then both be in a superposition until this third party intervened? Where does the chain of observation end? Does the entire universe remain in a state of suspended animation until a conscious mind somewhere takes a look? It seemed that the very act of knowing was somehow complicit in the act of creation. For decades, this measurement problem was the skeleton in quantum physics' closet. It was a philosophical embarrassment that most working physicists tried to ignore, adopting a shut-up and calculate mentality. The equations worked, so the interpretation could wait. But the nagging inconsistency wouldn't go away. A more physical, less philosophical explanation was desperately needed. The first glimmers of such an explanation came from a concept known as quantum decoherence. It was a brilliant and subtle idea that suggested the universe itself is the ultimate observer. The central premise is that no quantum system is ever truly isolated. That box containing Schrödinger's cat isn't a perfect fortress. Air molecules bounce off its exterior. Thermal radiation leaks in and out. Its own gravity ever so slightly perturbs the space around it. Each of these tiny, seemingly insignificant interactions is a form of measurement. Imagine the wave function of the cat, that perfect, fragile superposition of alive and dead, as a pure, coherent musical note ringing in an empty hall. Decoherence is what happens when you open the doors to a bustling city street. The sound of traffic, the chatter of crowds, the wind, all of this environmental noise immediately floods the hall. The pure note is instantly overwhelmed, its coherence lost as it becomes entangled with every single air molecule, every dust mote, every distant vibration in the environment. Its pristine quantum information doesn't vanish, but it leaks out and spreads, becoming hopelessly diluted across an impossibly vast number of environmental particles. In a fraction of a nanosecond, the clean superposition of alive plus dead devolves into a messy, classical-looking mixture of alive or dead. The wave-like quantum nature of the cat is effectively erased by its constant, unavoidable conversation with the rest of the universe. Decoherence was a monumental step forward. It explained why times we don't see macroscopic objects like cats or scientists in a state of superposition. They are simply too large, too warm, too complex to remain isolated from their surroundings for any meaningful amount of time. Their quantum coherence is incredibly fragile and is lost almost instantaneously. It provided a physical mechanism for the transition from the quantum to the classical world, bridging the gap that had troubled physicists for so long. It showed how the definite world of our experience could emerge from the probabilistic quantum substrate without needing to invoke a special role for conscious observers. The environment in its chaotic and relentless interaction was the ultimate measuring apparatus. It seemed for a moment that the puzzle had been solved. The ghost had been exorcised from the machine. But a deeper look reveals that decoherence, for all its explanatory power, is not a final answer. It is a brilliant and essential piece of the puzzle, but it doesn't solve the core measurement problem. It simply sweeps it under a much larger rug. Decoherence explains how a superposition times appears, times to become a classical choice, how the alive plus dead state rapidly evolves into a state that looks like either alive or dead. However, it never explains how or why one of those specific outcomes, the cat actually being alive or the cat actually being dead, is ultimately selected. The information about all possibilities is still technically there, just smeared out across the entire universe in the form of fantastically complex entanglements between the cat and every particle it has ever interacted with. The universe, according to decoherence, evolves into a colossal superposition of living cat and an environment that has recorded a living cat plus dead cat, and an environment that has recorded a dead cat. It solves the problem of interference. We'll never see the two states overlap, but it doesn't solve the problem of outcomes. It doesn't tell us why our particular experience, our sliver of reality, contains the living cat and not the dead one. All it does is take the superposition that was once neatly inside the box and explode it outwards to encompass the entire cosmos. It replaces the mystery of the collapsing wave function with an even grander, more intractable mystery, the branching of worlds, a concept we know as the many worlds interpretation. By trying to eliminate the observer decoherence, inadvertently made the universe itself the system in superposition, splitting it into countless parallel branches with every quantum interaction. And so, the search for a resolution continued, driven by the persistent unease that something fundamental was still being missed. The core of the problem remained entanglement, that bizarre, intimate connection between particles that Schrödinger himself called the characteristic trait of quantum mechanics. This was the mechanism that tied the cat's fate to the atoms and the friend's fate to the cat's. It's a connection that defies our classical understanding of space. Two entangled particles once linked can be separated by billions of light years, yet they remain a single, unified quantum system. A measurement performed on one particle will instantaneously influence the state of the other faster than light could ever travel between them. Einstein famously derided this as spooky action at a distance, believing it pointed to a flaw in the theory. He argued there must be some hidden information, some local hidden variables that the particles carried with them, predetermining the outcome of any measurement. But experiment after experiment, most notably those inspired by physicist John Bell, proved Einstein wrong. There are no hidden instructions. The connection is real, non-local, and deeply woven into the fabric of reality. This is not just a curious feature. It is the engine of the quantum crisis. Entanglement is what allows the quantum weirdness of a single atom to infect a macroscopic atom. It is what allows the state of an observer to become linked with the system they observe. It is the very glue that holds the paradox together. Decoherence uses entanglement with the environment to explain the appearance times of collapse. But it's entanglement itself that lies at the heart of the mystery. The interconnectedness of things was far deeper and stranger than anyone had imagined. We found ourselves at a profound impasse. The classical idea of a single pre-existing objective reality accessible to all observers in the same way was failing. The act of measurement of interaction seemed not to times reveal times a property of the world, but to somehow times create times it. Attempts to patch the theory to cleanly separate the observer from the observed had led to absurdities like infinite regress or a splintering multiverse. We were forced to confront a startling possibility. Perhaps the flaw was not in our theories, but in our most basic questions. We kept asking, what is the true objective state of the cat? As if that question had a meaning independent of any observer. We assumed that reality was a singular, monolithic entity. But what if this was the original sin? What if reality itself is not a monologue delivered by the universe, but a dialogue? A dialogue that can only happen when one part of the universe interacts with another. What if the very notion of a thing's properties only has meaning in relation to something else? This was the radical shift in perspective that was needed. A move away from a God's eye view of the universe and toward a universe built entirely on relationships. And so we find ourselves adrift, caught between two impossible shores. On one side lies the rigid certainty of the Copenhagen interpretation, a world neatly bisected between the quantum and the classical, a division policed by the mysterious and ill-defined act of measurement. It offers a pragmatic solution, a way to calculate and predict, but at the cost of a coherent story about reality itself. It erects a wall and tells us not to ask what lies on the other side. On the other shore is the breathtaking, perhaps terrifying expanse of the many worlds. A vision of cosmic profligacy, where every quantum choice splinters reality into an infinity of parallel universes, each one perfectly real, each one carrying a version of you. It offers a seamless mathematical narrative, but demands we accept a cosmos of unending duplication, a concept so vast it strains the very limits of belief. For decades, physics has been locked in this schism, a philosophical Cold War fought in the quiet language of equations. We were presented with a choice, a reality that is incomplete, or a reality that is incomprehensibly infinite. But what if this choice, this fundamental dilemma that has haunted quantum theory since its birth, is built upon a flawed premise? What if the mistake was made at the very beginning in the questions we chose to ask? Challenging a century of assumptions, a new voice began to articulate a third path, a way, not between the two shores, but through them. This was the voice of Italian physicist Carlo Rovelli, a thinker who proposed that to solve the quantum enigma, we needed a revolution in perspective as profound as Einstein's relativity. He suggested that the problem wasn't with the electron or the cat or even the observer. The problem was with our stubborn, deeply ingrained classical insistence on the word is. We ask, what times is times the state of the particle? We demand to know its absolute properties, its true and final nature, independent of anything else. Rovelli's breathtakingly simple yet earth-shattering proposal was that this question has no answer because it is the wrong question to ask. The universe, he argued, does not deal in absolutes. It deals in relationships. This is the genesis of Relational Quantum Mechanics, or RQM. It isn't an interpretation that adds new mathematics or postulates strange new realities. Instead, it is a radical rereading of the standard quantum formalism, an instruction to see the familiar equations through a new relational lens. At its heart is an idea that resonates with the truth we experience every day. Consider the concept of speed. You are in a train moving smoothly along the tracks. You toss a ball into the air and it falls straight back into your hand. From your perspective, its velocity forward is 0. But for someone standing on the platform watching your train race by that same ball is a projectile hurtling through space at 100 kilometers per hour. Who is right? What times is times the ball's true speed? The question is meaningless. There is no absolute speed. There is only speed times relative to u times, and speed times relative to the person on the platform asterisk. Both descriptions are correct. Both are valid accounts of reality from different points of view. We have long accepted this for motion thanks to Galileo and Einstein. Rovelli invites us to take the final courageous step to accept that this same principle applies to the very existence of things, to the fundamental properties of matter itself. According to RQM, a quantum system, an electron, a photon, an atom, does not possess intrinsic absolute properties waiting to be discovered. Its properties like spin or position only become definite and real times in relation times to another system that it interacts with. Before an interaction, the electron isn't in a fuzzy probabilistic cloud of maybe spin up and maybe spin down. That cloud, that wave function we have struggled with for so long, is not a description of the electron itself. It is a description of the times information times one system has about another times before times they have spoken to each other. It is a catalogue of potential answers to questions that have not yet been asked. The moment of interaction is the moment a question is posed. When your measuring device interacts with the electron answers, "My spin is up," but that answer is not for the whole universe to hear. It is a private message, a piece of reality actualized exclusively times for the measuring device asterisk. For your detector, the electron's spin times is times now up. This is a fact. A new piece of reality has been written. But for a different system, one that has not yet interacted with that electron, it remains a superposition of possibilities. Reality in this view is not a grand universal declaration. It is a vast and intricate network of private conversations. This elegantly and powerfully dissolves the observer problem that has plagued physics for a century. The issue was never about human consciousness. It was never our fragile biological minds that possessed the strange power to collapse wave functions. We fell into that trap because we as physicists were the ones performing the experiments, so we mistakenly privileged our own role. RQM removes us from that special central position. An observation in this new language is not a profound act of conscious inquiry. An observation is simply an interaction. Any interaction, anywhere, at any time. When a photon from the sun strikes a dust mote in the interstellar void, an interaction occurs. The photon's properties become definite times relative to the dust mote times, and the dust mote's properties become definite times relative to the photon asterisk. A tiny localized piece of reality has been forged in that silent, unseen transaction. The universe is not waiting for a conscious being to look at it in order to exist. It is constantly happening to itself, a cascading self-referential web of interactions where every system is an observer for every other system it touches. The cosmos is a cacophony of observation, a relentless exchange of information where particles, atoms, stars, and galaxies are continuously defining reality for one another. The world is not a static stage upon which things happen. The world times is times the happening. It is the sum total of these countless interlocking relationships. With this new framework, we can return to those haunting paradoxes like Wigner's friend and find they are not paradoxes at all. They are simply illustrations of this fundamental relational truth. Imagine the scene again. Your friend is inside a sealed laboratory about to measure the spin of an electron. Before she does, from her perspective, the electron is in a superposition of spin up and spin down. For you, waiting outside the situation is more complex. The entire laboratory, the friend, the electron, the measuring device, is one large quantum system. From your isolated viewpoint until you interact with it, the lab itself is in a superposition. There is a version of the lab where your friend has measured spin up and is smiling, and a version where she has measured spin down and is frowning. The old interpretations forced us into an impossible position. Copenhagen would say the collapse happened when your friend looked but offered no clear rule for why her observation was special. Many worlds would say that at the moment of measurement, the universe split in two, creating both a smiling and a frowning friend in separate realities. RQM calmly steps through the looking glass and presents a third, more elegant solution. It declares that both you and your friend are describing reality correctly from your own perspectives. Inside the lab, your friend interacts with the electron. In that interaction, a fact is established times for her asterisk. Let's say she measures spin up. In her world, relative to her and her equipment, the electron's state is no longer ambiguous. It times is time's spin-up. This is her reality. But for you outside, no new information has crossed the boundary of the lab. You have not yet interacted with your friend or her result. Therefore, from your perspective, the lab remains a coherent quantum superposition. The friend plus electron system is a complex wave of possibilities. You are not wrong, and she is not wrong. You are simply describing the same event from two different relational standpoints between which no information has yet been exchanged. There is no contradiction any more than it is a contradiction for one person to say a ball's speed is 0, while another says it is 100. The paradox only arises if you cling to the classical illusion that there must be one single absolute God's eye view of the situation that is true for everyone everywhere at all times. RQM forces us to let go of that comforting but ultimately false anchor. This is a profound conceptual leap, a deep restructuring of our understanding of existence. For centuries, the dream of physics from Newton to Einstein was to find that universal vantage point. We sought a theory of everything that would allow us to stand outside the cosmos, metaphorically speaking, and describe it in its totality with a single, unambiguous set of equations, a final objective truth. Relational quantum mechanics tells us that such a vantage point does not exist. It is a fiction. It is a logical and physical impossibility. You can never stand outside the universe to describe it because you are by definition a part of it. You are one of the systems within the network. Therefore, any description you provide is necessarily a description from the inside, an account of the relationships you have with the rest of the world. There is no absolute universal state of the cosmos. There is no master wave function for all of reality. There is only the fantastically complex network of all the relative states, the interwoven tapestry of countless perspectives, each one real, each one valid, each one defined by the interactions that bind it to the rest. Reality is not a mountain solid and unchanging that we all view from different angles. It is a dance, and every dancer's movement only has meaning in relation to the movements of every other. This vision transforms the universe from a collection of static objects with pre-existing properties into a dynamic, effervescent reality of pure becoming. Things do not times have times properties. Properties times emerge, times from interactions. An object in isolation is a ghost. It is a set of potentialities. It is only when it touches another that it solidifies, that it gains definition, that at times becomes asterisk. And this becoming is not a one-time event, it is continuous. Every system is constantly updating its description of the other systems it is coupled with. Information is the currency of existence, and interaction is the mechanism of exchange. The universe then is not made of particles, it is not made of energy or fields. The universe is made of information, information that systems have about other systems. This information is physical, it is real, and it constitutes the very fabric of our world. We are not observers looking at a separate reality. We are nodes in a cosmic network woven from the threads of these quantum relationships. Our own reality is the sum of the physical information exchanged between the constituents of our bodies and the rest of the cosmos. Think of it like a conversation that has been going on for 13.8 billion years. Every particle is a participant. When a cosmic ray from a distant supernova finally reaches Earth and strikes an atom in our atmosphere, a new sentence is spoken in that conversation. A new fact is created, a new relationship established. The atom now has a definite state relative to the ray and the ray relative to the atom. This single event doesn't define a universal reality, but it adds one more thread to the impossibly intricate tapestry. It is a local truth, a piece of a mosaic so vast that no single perspective could ever take it all in. We are embedded within this mosaic. Our consciousness, our thoughts, our very existence are higher order patterns that emerge from this ceaseless fundamental chatter. We are not the authors of reality, nor are we merely its audience. We are a part of the story written in the same relational ink as everything else. We are the universe in one of its countless forms, becoming aware of itself through this very process of interaction. This relational framework, however, opens up a new set of profound and challenging questions. If reality is a patchwork of perspectives, how do we reconcile them? We see a consistent, stable world around us. The moon is in the sky for everyone, not just for me when I look at it. How does this shared classical world emerge from this bubbling quantum foundation of relative facts? Rovelli argues that we live in a world of abundant, redundant information. We are all interacting with the same systems, the same photons from the moon, the same air molecules, the same gravitational fields. Our individual perspectives, our separate realities, are constantly being correlated and cross-referenced through a shared environment. We agree on the position of the moon because we are all, in essence, reading from the same page, a page written by billions of years of consistent, stable interactions. Our shared classical reality is not a fundamental property of the universe. It is an emergent feature, a consequence of being macroscopic systems swimming in a dense sea of common information. But this raises an even deeper puzzle. This entire framework is built upon the idea of interactions and the information they create. But what is information without time? And what is time within this relational network? If there is no universal clock, no master metronome ticking for the entire cosmos, does time itself become relational? Does each system experience its own flow of time born from the sequence of its own interactions? By dismantling the idea of a universal now and a singular reality, RQM seems to point towards a world where the fabric of space-time itself might be woven from these quantum relationships. We have moved from the paradoxes of measurement to the very nature of existence, and in doing so, we find ourselves at the edge of an even greater mystery, the quantum origin of space and time. We have found a potential path out of the quantum labyrinth, only to discover that it leads directly into the heart of an even more enigmatic territory, a place where the deepest questions of quantum theory merge with the greatest questions of cosmology. And so the serene clockwork universe of our ancestors is gone, shattered. In its place, relational quantum mechanics offers us not a new machine, but a shimmering ghostly tapestry woven from interactions. We have been forced to abandon the comforting port of a single objective reality, a solid shore that exists independent of any ship. Instead, we find ourselves adrift on a strange and boundless ocean, where the map is drawn only as we sail, and every voyager charts a different, yet equally valid course. This is the moment the true vertigo sets in. If the properties of a particle, its very state of being, are only defined when it interacts with another system, what does this do to our shared world? The chair you are sitting on, the screen you are watching, the very air filling your lungs. Our intuition screams that these things are real, unambiguously, and for everyone. They are public facts. Yet the foundation upon which they are built, the quantum world, insists that facts are private affairs, whispered secrets exchanged between two interacting partners, and no one else. This is the great terrifying and exhilarating chasm RQM opens before us. It demands we ask a question so fundamental it feels almost blasphemous. Is the universe you experience truly the same as the one I do? To navigate this new territory, we must first learn its language. Let's return to our brave observers, Wigner and his friend, for their predicament is now our own. From the friend's perspective inside the isolated laboratory, the quantum event has concluded. The atom has decayed, or it has not. The cat in that infamous thought experiment is definitively alive or dead. For the friend, this is a concrete, irreversible piece of information, a new fact that now defines their reality. But for Wigner, standing outside, nothing has changed. The entire laboratory, the friend, the atom, the detector, remains a single, colossal quantum system, suspended in a delicate superposition of all possible outcomes. According to the unwavering laws of quantum mechanics, Wigner's description is perfectly correct. And according to those same laws, the friend's description is also correct. This is not a paradox to be solved, but a new truth to be accepted. We have two true statements about the same event that are mutually exclusive. Truth, it seems, has become perspectival. Reality has acquired an address. There is a reality for the friend and a reality for Wigner. They are not illusions. They are not matters of opinion or belief. They are both physically accurate descriptions, validated by the mathematics that governs the cosmos. Imagine two people describing a mountain. One stands to the north, seeing a sheer icy cliff face. The other stands to the south, seeing a gentle forested slope. Both are giving true accounts of the mountain. We are comfortable with this because we can imagine walking around it, integrating all perspectives into a single three-dimensional object. We believe in the existence of the mountain in itself. RQM tells us that at the fundamental level, there is no walking around. There is no system in itself. There is only the view from the north and the view from the south. The relationship times is times the reality. There is no deeper absolute thing in itself to which all these relative facts refer. This, however, raises a terrifying spectre that has haunted philosophers for centuries, the ghost of solipsism. If reality is only defined relative to me through my interactions, does that mean the universe is merely a figment of my imagination? Does your existence depend on my observation of you? This is perhaps the most profound and common misunderstanding of RQM, and we must confront it directly. The theory is not reality is relative to consciousness. It is reality is relative to the interacting physical system. An observation is not a mental event, it is a physical interaction. Full stop. A photon striking a detector is an observation. An electron bumping into another electron is an observation. Your mind, your consciousness, your human experience are not granted any special privileged role in creating the world. You are a complex physical system, a collection of quantum fields, and your interactions have the same status as those of a rock, a star, or a dust mote. The relational view is not subjective. It is radically objective, but it redefines what objectivity means. It states that any times physical system can be an observer and have a perspective. The universe is not a monologue delivered by your consciousness. It is a cacophony of countless simultaneous conversations between every particle and every other particle it touches. Your reality is real. My reality is real. The reality of the pebble on the beach as it is struck by a wave is real. They are all different. They are all valid. The world is not a dream in a single mind. It is a near infinite network of physical relationships, each one a nexus of truth, each one a point of view. The illusion is believing there's a single divine vantage point from which the entire network can be seen at once. There is no outside. We are all nodes within the network. But how then, out of this seemingly chaotic, fragmented foundation, does our stable classical world emerge? How does this kaleidoscope of private facts coalesce into the shared reality we all seem to inhabit? You and I can agree that the moon is in the sky. We build bridges that do not flicker in and out of superposition. Our macroscopic world feels solid, reliable, and decidedly non-relative. The answer lies in the sheer density and consistency of interactions. As a large, complex system, you are not isolated like a friend in their lab. You are in a constant, furious, and unrelenting state of interaction with your environment. Trillions upon trillions of photons from the room's lights are bouncing off you and into my eyes every second. Air molecules are colliding with your skin. The gravitational pull of the Earth is a ceaseless communication between every atom in your body and the planet. This process, known as decoherence, is the key. Any quantum superposition you might possess is almost instantly leaked into the environment through these countless interactions. The information about your state, your position, your momentum is copied and copied and copied again across a vast web of particles. Your private facts become public knowledge at an astonishing rate. Think of it as a cosmic consensus. When I look at you, I am not just interacting with you. I am interacting with the light that bounced off you, which interacted with the air it traveled through, which is part of the room which is anchored to the Earth. My perspective and your perspective become correlated, locked into alignment by our shared, overwhelming interaction with the same environment. We agree on the state of the room because we are both so deeply entangled with the room itself that our realities are forced into a common narrative. This shared classical world is not a fundamental property of the universe. It is an emergent phenomenon. It is a stable pattern of correlations, a public reality that arises for a community of systems us that are all interacting with each other in a stable and predictable way. It is a bubble of common ground in a vast sea of relative possibilities. We are the products of a profoundly stable set of relationships, a kind of gravitational gyroscope of mutual information that holds our shared experience steady. Our world feels solid not because it is built on a solid absolute foundation, but because it is woven together by an impossibly dense and self-consistent web of relations. It is crucial here to clarify another common point of confusion. RQM is not simply saying that our knowledge times, is limited, and that a system is in a superposition only because we don't know its true state. This is an epistemological argument, an argument about what we know. RQM makes a far more radical ontological claim, an argument about what times is asterisk. It posits that before an interaction, the properties of a system are not just unknown, they are non-existent, they are undefined. The electron does not have times a definite spin before you measure it. The act of measurement, the physical interaction, is what brings that property into being, times relative to you, the measuring device asterisk. There is no hidden underlying reality that we are failing to see. The relationship is all there is. The information exchanged in an interaction is not a pale reflection of a deeper truth. It is the truth itself. The map for each observer times is times the territory. This move is what frees quantum mechanics from the paradoxes that have haunted it for a century. The measurement problem, the question of why the fuzzy quantum world magically collapses into a definite state upon observation, simply dissolves. There is no collapse. There is only the updating of one system's information about another when they physically interact. For Wigner, outside the lab, the system evolves perfectly according to the Schrödinger equation, a smooth wave of possibilities. For the friend, inside an interaction occurred, a new fact was established. Both are correct. There is no contradiction because they are describing reality relative to different systems. So what happens when these two realities finally meet? What happens when Wigner at long last opens the door to the lab and asks his friend what she saw? This is the moment of reconciliation. The interaction between Wigner and the friend in the lab now forces their two realities to become correlated. If the friend says, the atom decayed, that information propagates to Wigner. Wigner's description of the world, which previously held the friend and atom in superposition, must now be updated. The wave of possibilities, times for him, times now, resolves into the single fact communicated by the friend. But this does not mean his previous description was wrong. It was the complete and accurate description of the world times relative to him times before this new interaction took place. The consistency of the world is maintained. Quantum theory guarantees that the information exchanged will never be contradictory once observers are in communication. The friend will never see the atom decay and then tell Wigner it did not. The network of relations is self-policing. Facts, once they become public within a subsystem through interaction, are stable times for that subsystem asterisk. When Wigner opens the door, he is not uncovering a pre-existing truth that was there all along. He is expanding his network of relations. He is joining the consensus that was already established inside the lab. His reality, once separate and described by a superposition, now aligns with the friends described by a definite outcome. Two streams of reality merge into one larger, more correlated flow. We are left staring into the abyss of a universe constructed not from absolute things, but from infinite intersecting perspectives. A world where existence itself is a dialogue. You are a nexus of relationships. Your reality is the sum total of the physical questions the universe has asked of you and the answers your body has given. Every photon that strikes your retina, every sound wave that vibrates your eardrum, every atom you touch is a moment where your reality is co-created with the rest of the cosmos. We are not spectators in a grand cosmic theatre watching a play that was written long ago. We are the actors, and the script is being written line by line through our very presence, through our every interaction. This is the profound and for some deeply unsettling consequence of taking quantum mechanics at its word. It removes us from the center of existence, dethroning not just humanity, but the very idea of a central objective viewpoint. Yet in its place, it offers something far more intimate and beautiful. A universe that is not a cold dead object to be observed, but a living dynamic network of which we are an inseparable and active part. Our sense of self, our perception of a solid world, our feeling of a shared journey through time, all of these might be the magnificent and stable illusions that emerge when a near infinite number of quantum conversations all begin to sing in harmony. The question that remains, the one that will carry us into the final act of our exploration, is what orchestrates this cosmic symphony. If reality is a web of information, where does the information come from, and what ultimately is it about? And so we arrive at the Great Schism, the conceptual chasm that has divided physicists for a century. We have lingered in the strange suspended reality of Wigner's friend, trapped inside a laboratory where a quantum measurement has occurred, yet from our external viewpoint, the entire system, friend particle and measuring device remains a single, colossal superposition. It is a paradox born from a simple, devastatingly profound question. Where does the quantum world end and our solid classical reality begin? The Copenhagen interpretation, the venerable grandfather of quantum thought, drew a line in the sand, an arbitrary boundary it called the Heisenberg cut, separating the ghostly realm of potentialities from the definite world of measurement. But it never told us where that line was or why it existed at all. It was a rule, not an explanation. Other theories, like the many worlds interpretation, chose a different path, suggesting that every possible outcome does happen, each one branching off into a new parallel universe, a solution of breathtaking scope, yet one that burdens us with an infinite, unseeable cosmic baggage. For decades, we have been forced to choose between an arbitrary rule and an infinite reality. But what if the problem was never the physics but the question itself? What if the search for a single, absolute, universally true state of affairs, a God's eye view of the universe, was the original sin that led us into this paradoxical maze? Relational quantum mechanics proposes a breathtakingly elegant escape. It does not draw a line, it erases it. It does not multiply worlds, it simplifies our own. It suggests the error was in believing that a system possesses absolute intrinsic properties in the first place, waiting to be passively observed. Instead, it posits that properties are only ever realized, only ever made concrete in the act of interaction. Measurement, that mysterious and violent event that seemed to tear reality asunder, is demoted. It is no longer a magical invocation performed by a conscious observer or a giant classical apparatus. In the relational view, a measurement is simply one physical system acquiring information about another. It is an interaction, nothing more, nothing less. An electron interacting with a phosphorus screen is a measurement. A photon striking a silver halide crystal is a measurement. A dust mote in the void of space being nudged by the cosmic microwave background is a measurement. The universe in this telling is a ceaseless, intricate symphony of interactions, a grand network of systems defining each other moment by moment. The observer is not special. You are not special. I am not special. A human scientist, a cat in a box, a Geiger counter, or a single helium atom are all on a fundamental level just physical systems capable of entering into a correlation with another system. And in that moment of correlation, reality for them becomes definite. The collapse of the wave function is not a universal objective event that ripples through the entire cosmos at once. It is a local, private, and relational affair. It happens for you when you interact with the system. It happens for the detector when it interacts with the system. But it does not happen for someone who has not yet interacted with either of you. This is the key that unlocks the door to Wigner's sealed laboratory. Let us return to that unsettling scene, but this time we will view it through the relational lens and watch as the paradox dissolves not into a puff of logic, but into a richer, more profound understanding of reality itself. Inside the lab, the friend measures the spin of a particle. Let us say she finds it spin up. From her perspective, an interaction has occurred. Her state has become correlated with the particle's state. The quantum uncertainty for her has vanished, crystallizing into a single, unambiguous fact recorded in her notebook and in the configuration of her own neurons. The wave function relative to her has collapsed. She now lives in a world where the particle is and always has been spin up. Her reality is stable, consistent, and classical. There is no paradox for her. She would laugh at the suggestion that she is somehow in a ghostly blend of states. Yet for Wigner, standing outside the situation is profoundly different. He has not interacted with the particle, nor has he interacted with his friend or her measuring device. From his vantage point, the thick walls of the laboratory have maintained perfect quantum isolation. Therefore, according to the inviolable laws of quantum mechanics, the entire contents of the room, the particle that is spin-up, the friend who has seen it is spin-up, the device that recorded it as spin-up, are now entangled with each other, forming one vast quantum system. And this entire system, from Wigner's perspective, is still in a superposition. It is a complex quantum state describing both particle is spin-up and friend saw spin-up, and particle is spin-down, and friend saw spin-down. For Wigner, his friend is not in a definite state. She exists in a quantum haze, a superposition of having two different memories, two different experiences at the same time. Who is right? Is the particle's spin definite, or is it not? Is the friend in a single state of mind, or a ghostly blend of two? The old way of thinking forces us to declare one of them wrong, to find a contradiction. But relational quantum mechanics simply smiles and says they are both right. They are both describing the exact same reality but from two different perspectives, relative to two different sets of interactions. The friend's description of the world is true times for her times, and for any other system inside the lab that has interacted with the particle. Wigner's description is true times for him, times and for any other system that has remained isolated from the lab's interior. There is no single absolute truth of the matter, just as there is no absolute state of motion in the universe. The contradiction was an illusion, an artifact of our deeply ingrained classical intuition that there must be one story of the world that is true for everyone. RQM asks us to let go of this comforting but ultimately false notion of objectivity. Reality is not a monolithic sculpture that we all view from different angles. It is a tapestry of correlations woven by interactions, and the world you experience is the pattern that has been woven relative to you. When Wigner finally opens the door to the laboratory and asks his friend, "What did you see?" a new interaction occurs. At that moment, Wigner's state becomes correlated with the friend and particle system, and only then, relative to Wigner, does the grand superposition collapse into a single definite outcome. He will find his friend in a perfectly definite state with a definite memory of seeing a definite result, say spin up. From his new perspective, the entire history of the experiment will now be consistent with that outcome. But this collapse, this crystallization of fact, happened times for him, times the moment he interacted. For his friend, it happened much earlier. The universe did not conspire to have a single universal now in which the quantum jump occurred. The now of the collapse is personal. It is relational. This might sound like philosophical sleight of hand, a semantic trick to escape a century-old problem, but its implications are deeply physical, and they echo in the most advanced frontiers of technology we are currently exploring. Consider the burgeoning field of quantum information science. We speak of qubits, the fundamental units of quantum computers, as holding information in a superposition of 1 and 0. But what times is times this information? The relational perspective gives us a powerful new grammar. Quantum information is not a property that a particle has. It is a description of the potential correlations a particle could establish with other systems. A qubit in a perfect superposition is a system that has not yet established a correlation about its state with anything else in the universe. It holds a promise of information, a potential to relate. The very act of a quantum computation is the careful, deliberate choreography of these interactions, weaving a complex tapestry of entanglement of structured relations to solve problems that would take a classical computer billions of years. And what of the great nemesis of quantum computing, the dreaded phenomenon of decoherence? This is the process by which a quantum computer loses its precious quantum nature and collapses into a mundane classical state, destroying the day-thing's power, computation. From the old perspectives, decoherence is a mysterious intrusion, the noisy classical world corrupting the pristine quantum system. But from the relational viewpoint, it is perfectly natural. Decoherence is nothing more than your quantum computer accidentally interacting with its environment. A stray photon, a vibrating atom in the substrate, a fluctuation in an electromagnetic field, each one is a tiny Wigner, opening the door to your laboratory without your permission. Each interaction establishes a new correlation, a new relation, measuring the state of your qubits and making their state definite relative to the environment. The information you tried to carefully isolate and control leaks out, becoming a fact relative to the outside world, and the quantum potential you were harnessing evaporates. Quantum error correction, then, is the art of building shields against these unwanted relations, of preserving the informational virginity of the system relative to its environment, so that it only speaks to the systems you intend. RQM provides the fundamental conceptual bedrock for why this is both necessary and so incredibly difficult. It tells us we are not fighting a mysterious force. We are fighting the universe's relentless tendency to relate, to interact, to share information. This relational nature extends to even the most mind-bending of quantum phenomena, like teleportation. When we teleport the state of a qubit, we are not sending matter through space. That is the stuff of science fiction. Instead, we are using the strange, pre-existing correlation of entanglement to transfer relational information. We perform a measurement on a particle here, which is entangled with a particle far away. This measurement establishes a relationship between the particle we want to teleport and our local entangled particle. Because of the deep non-local nature of their shared history, this new relationship instantly informs the state of the distant particle relative to its twin. We then send some classical information, the result of our measurement, to our colleague at the distant location, telling them how to interact with their particle to complete the transfer. We are not moving a thing, we are moving a set of relations. We are teaching a distant particle how it is supposed to relate to its new surroundings based on the relations of the particle we started with. The entire process is a testament to the idea that quantum mechanics is not a theory of things, but a theory of information, a theory of how physical systems come to know about each other. And it is here, in this grand vision of a universe built not on absolute substances, but on a web of relations, that we find the most astonishing and profound resonance with the other great pillar of modern physics. For a century, quantum mechanics and Albert Einstein's theory of general relativity have stood apart, two magnificent but seemingly incompatible descriptions of reality. One governs the microscopic world of particles and probabilities with breathtaking accuracy, while the other describes the macroscopic world of planets, stars, and galaxies of gravity and the curvature of space-time with equal precision. The search for a unified theory, a quantum gravity, is the holy grail of theoretical physics. And while RQM is not itself a theory of quantum gravity, it reveals a shared philosophical foundation so deep, so powerful, that it feels like the first glimmer of dawn on a new horizon. It suggests that the two theories are not just speaking different languages. They are telling two parts of the same epic story. Think about the core lesson of Einstein's relativity. It is the demolition of absolutes. Before Einstein, we believed in an absolute space, a fixed, invisible grid against which all motion could be measured. We believed in an absolute time, a universal clock ticking at the same rate for everyone everywhere in the cosmos. Relativity shattered this. It showed us that space and time are not a static stage on which the cosmic drama unfolds. They are dynamic actors in the drama itself. There is no absolute now. Whether two events are simultaneous depends entirely on your state of motion relative to them. The rate at which your clock ticks, the very flow of time you experience, depends on your velocity and the strength of the gravitational field you are in. A clock on a mountaintop literally ticks faster than a clock at sea level. An astronaut traveling near the speed of light experiences time far more slowly than we do on Earth. Every fundamental property of space-time duration, length, simultaneity was revealed to be nothing more than a relationship between an observer and the thing being observed. There is no view from nowhere. Do you see the parallel? Do you feel the ground shifting beneath your feet? Relational quantum mechanics is doing for the properties of matter what Einstein did for the properties of space-time. Just as relativity says, there is no absolute time, RQM says there is no absolute state of a quantum system. Just as the duration of a second is a relationship between you and a clock, the spin of an electron is a relationship between you and that electron. The universe seen through this combined lens is fundamentally and profoundly relational from top to bottom. From the gravitational whisper passing between two galaxies, warping the very fabric of space-time that separates them, to the fleeting quantum interaction between two photons, instantiating a shared moment of polarization, the story is the same. It is a universe of interactions of perspectives. The solid world we see around us is not the bedrock of reality. It is a consensus, a thick web of stable classical relationships that have been established over eons between us and the macroscopic objects around us. We are so deeply embedded in this web of correlations that we mistake it for the entire world, forgetting the seething, indefinite quantum ocean that lies beneath. This is not merely a philosophical curiosity, it is a powerful new map for the explorers of fundamental physics. It suggests that any successful theory of quantum gravity must itself be relational. It must describe a world where space-time geometry itself can exist in a superposition where the causal relationships that define past and future are not fixed, but are established through quantum interactions. It points toward a reality where the fabric of the cosmos is woven from a network of quantum information, where each link, each correlation, is a tiny stitch holding space and time together. We are no longer just asking how matter behaves within space-time. We are beginning to ask whether space-time itself is an emergent property of these fundamental quantum relations. This is the new frontier, the breathtaking landscape that opens up when we finally let go of our classical attachment to a single, absolute reality. We are left with a universe that is more subtle, more interconnected, and ultimately more participatory than we ever dared to imagine. But this new vision, for all its elegance and power, leaves us with a dizzying, vertiginous question. If the properties of an object only exist when it is interacting, if a particle's state is only defined relative to another system, then what times is times a physical system when it is not interacting with anything? What is an electron alone, in the void with nothing to relate to? Does it even exist in any meaningful sense? By dissolving the paradox of measurement, have we inadvertently stumbled upon an even deeper mystery, the nature of existence itself? We have peeled back the layer of the observer, only to find ourselves staring into the very heart of being, and the silence that greets us is as unnerving as it is profound. And so, the last pillar of the old world crumbles. The final, most cherished assumption of a single objective, universally agreed upon reality, a truth that exists independently of us, quietly dissolves. It doesn't vanish into a fog of subjectivity or chaos, but transforms into something far more intricate, more dynamic, and perhaps more beautiful. We have journeyed from the clockwork perfection of Newton's cosmos, a universe of solid objects following predictable paths through the strange and unsettling landscape of the quantum revolution. We've wrestled with particles that are also waves, with cats that are simultaneously living and dead, and with entangled twins communicating instantaneously across impossible voids. Each step forced us to surrender a piece of our intuition, to abandon the comfortable assumptions baked into our very language and perception. Now standing at the precipice of relational quantum mechanics, we are asked to take the final leap. We are asked to accept that the universe is not a monologue delivered by an indifferent author, but a grand, interconnected dialogue. This is the ultimate consequence of our century-long interrogation of the quantum realm. Reality is not a thing to be observed, but a relationship to be had. The properties of an electron, its spin, its position, are not inherent labels it carries through the void. They are answers it gives, moments of definition that spark into existence only when it interacts with something else, with another particle, a measuring device, or with you. Before that interaction, the question of its true state is not just unknown, it is meaningless. The universe from this perspective is not a museum of pre-existing facts waiting for us to catalogue them. It is an immense, sprawling network of these interactions, a shimmering web where each node, each system, only gains definition relative to the other nodes it touches. We are not external observers peering into a separate objective world. We are ourselves nodes within this cosmic network, inextricably woven into the very fabric of reality we seek to understand. Our act of measurement, our observation, is not a passive glimpse but an active participation, a conversation that co-creates the properties we perceive. The world described by one observer is a complete and consistent world, just as the world described by another observer is. The revolutionary insight of RQM is that these descriptions, while both perfectly valid, do not have to be the same. The paradox of Wigner's friend, where one observer sees a quantum superposition and another sees a definite outcome, is not a paradox at all. It is simply the universe speaking in different relational tongues. For the friend inside the lab, the interaction has occurred, a fact has been established, a relationship formed. For Wigner, outside the lab, the entire system, friend and particle alike, remains an unasked question, a single quantum state suspended in possibility. There is no absolute God's eye view to resolve the discrepancy, because such a view does not exist. There is no universal ledger of cosmic facts. There are only the countless interlocking perspectives, each one a self-consistent bubble of reality generated by physical interaction. This is a profound shift in our cosmic address. We are no longer tenants in a pre-furnished universe. We are the co-architects of its unfolding, one interaction at a time. The universe is not a story being told to us. It is a story we are telling together through the simple physical act of touching, seeing, and measuring. But how do we move such a staggering idea from the realm of philosophical interpretation to the rigorous domain of experimental science? How do we test a theory that claims absolute reality is an illusion? The challenge is immense as RQM by. Its very nature often makes the same experimental predictions as standard quantum mechanics within a single observer's frame of reference. The difference lies in how it reconciles the descriptions between different observers. The cutting edge of this pursuit lies in pushing the Wigner's friend thought experiment out of the imagination and into the laboratory. Physicists are now designing incredibly complex experiments using quantum computers and entangled photons to create nested layers of observation. Imagine a scenario where a quantum bit, a qubit, acts as the friend. A first layer of measurement probes this qubit, establishing a relational fact for that specific measuring device. Then a second encompassing measurement acting as Wigner is performed on the entire system, both the qubit and the first device. The goal is to search for interference patterns. If the first measurement truly collapsed the wave function in an absolute universal sense, then no quantum interference should be possible for the second larger measurement. But if RQM is correct, and the outcome of the first measurement is only a fact relative to that first device, then from the perspective of the second Wigner measurement, the entire subsystem should still be in a quantum superposition. Finding evidence of this superposition, a telltale interference pattern at the level of the encompassing observer, would be a seismic event in physics. It would provide powerful, tangible evidence that outcomes are not absolute. It would mean that a fact of reality can exist for one system while remaining an open possibility for another. These experiments are pushing the boundaries of what is technologically possible, requiring unprecedented control over quantum systems to prevent the slightest environmental interaction, a stray photon, a whisper of heat from leaking information and destroying the delicate nested superpositions. The very difficulty of the experiment is a lesson in itself, highlighting how pervasively interactions define our world and how challenging it is to truly isolate one perspective from another. Beyond these intricate tabletop experiments, some scientists are beginning to wonder if the universe itself has already run a version of this test for us. Could cosmology offer a clue? The early universe was a hot, dense quantum soup, a system of pure interaction. As it expanded and cooled, structures formed and information became localized. Perhaps the large-scale structure of the cosmos, the distribution of galaxies, or the subtle temperature fluctuations in the cosmic microwave background radiation retain a faint relational memory of this era. Could there be subtle correlations in the sky that are best explained by a model where information was always observer-dependent, where there was never a single universal quantum state for the entire cosmos? This is highly speculative, a frontier of theoretical physics, where ideas are still being formed. Yet it captures the ambition of the relational program to see if the largest observable canvas we know reveals the same intimate perspective-dependent rules that we are now uncovering in the smallest of quantum labs. The quest is to find a place where the descriptions of two different vast cosmic observers, say our observable patch of the universe and another patch beyond our cosmic horizon, would diverge in a way we could infer a cosmic echo of Wigner's friend. This relentless drive to unify perspectives brings us to the holy grail of modern physics, the reconciliation of quantum mechanics and Einstein's theory of general relativity. These two great pillars of our understanding are famously incompatible. General relativity describes a smooth, dynamic space-time, a fabric that curves and warps in response to mass and energy. Quantum mechanics describes a world of discrete packets of probabilities and granular interactions. When you try to apply quantum rules to space-time itself, as you must in a black hole or at the Big Bang, the mathematics breaks down into nonsensical infinities. This is where RQM offers not just a philosophical shift, but a profound conceptual tool. General relativity at its heart is already a relational theory. The notion of a fixed, absolute background of space and time, Newton's stage, was abolished by Einstein. Space-time acts on matter, telling it how to move, and matter acts on space-time, telling it how to curve. It is a dynamic relationship. RQM proposes that the quantum world works the same way. There is no absolute pre-existing background of quantum states. There are only relationships. This shared relational nature provides a powerful bridge. Consider the problem of time in quantum gravity. When physicists write down the most fundamental equations that attempt to unite the two theories, the variable for time mysteriously vanishes. From a view from nowhere, looking at the entire universe at once, there is no evolution, no before, no after. This has been a deep and persistent puzzle. But from a relational perspective, it is exactly what we should expect. Time does not exist for the universe as a whole because the universe does not interact with any external clock. Time, RQM suggests, is an emergent property of interaction. It is the measure of change of one physical system relative to another, the swing of a pendulum, the oscillation of a cesium atom, the orbit of the Earth. Time is always internal, a property of a subsystem, not a universal parameter. By abandoning the idea of a universal now and a universal quantum state, RQM dissolves the problem. It suggests that the search for a fundamental universal time was a ghost hunt from the start, a relic of our classical intuition. A true theory of quantum gravity from this vantage point will not be a theory of things evolving times in time's time, but a theory of how the very phenomenon of time emerges from a timeless web of fundamental quantum relationships. And this brings us inevitably back to ourselves. If the universe is a web of interactions and reality is a tapestry of perspectives, what does that say about us? What is the observer in relational quantum mechanics? Critically, it is not a conscious mind. It is not a human or even a biological entity. An observer is any physical system that can interact with another system and form a stable correlation, a record of that interaction. A photon striking a photographic plate is an observation. A C-naught gate in a quantum computer is an observation. A rock at the bottom of the ocean, whose atomic structure is altered by the decay of a nearby radioactive element, has in a very real sense observed that decay. The universe is teeming with countless non-conscious observers, each one defining a small local set of facts through its physical entanglements. This demystifies the role of the observer, removing the magic of consciousness from the measurement problem. Consciousness does not collapse the wave function, interaction does. Yet this does not diminish the profound implications for our understanding of consciousness. On the contrary, it places it squarely within the natural physical world. We, as conscious beings, are extraordinarily complex systems of interaction. The human brain is perhaps the most sophisticated information processing, correlation-forming system we know of. Every thought, every perception, every memory is a cascade of physical interactions between neurons, a constant updating of our internal description of the world. RQM suggests that our conscious experience is a particularly rich and complex manifestation of the same fundamental process that happens everywhere in the cosmos. Our subjective reality is not an illusion, but it is also not a perfect mirror of some external absolute truth. It is the consistent, self-contained story woven from the trillions upon trillions of physical interactions that constitute our body and our brain. We are a perspective. We are a point of view physically instantiated. The feeling of being a unified self may be the emergent property of this continuous, coherent process of relational information exchange. The boundary between ourself and the world is not a sharp, immutable line, but a permeable membrane of interaction. The world informs us, and in our every action, in every measurement, we inform the world. We are not ghosts in the machine. We are the machine ceaselessly weaving ourselves into the fabric of the relational cosmos. We began our journey seeking a final objective truth, a single sentence that could describe the universe as it truly is. We end it with the realization that the universe is not a sentence, but a conversation with infinite participants. It is a cosmos built not of things, but of whispers, of exchanges, of relationships. We have been forced to trade the comfort of absolute certainty for the dizzying, awe-inspiring vision of a participatory reality. The quest to understand is no longer a passive act of discovery, but an active process of engagement. There is no final answer to be found by standing apart from the world. There are only deeper questions to be asked, and richer relationships to be formed by stepping ever further into it. The mystery of existence has not been solved, but it has been transformed, and our part in it, our responsibility, our potential, has become infinitely greater. The story of the universe is not written. It is being co-authored right now in the endless dance of interaction that connects everything to everything else.